Hello. I bought a couple of these little VU meters for an audio project. I believe I paid something around just above $5 each. I'll leave a link in the description to the seller. They are quite small. You can try seeing here. 35 millimeters on each side. And what is this? 34 millimeters. They are quite deep though. It's about 37 and a half. And there's some connections on the back here, so probably need more like maybe 45 millimeters deep. So they appear to be made in just one piece, but I do believe they split here, just behind this bracket here. I think you can take them apart. And we have 4 connections on the back. I believe the 2 outer ones here are for the light, and the 2 in the center here marked minus and plus. They're probably for the meter. The listing specified it at 12 volts for the light, but I think we should try test it and see how low would it go, because you don't want your hi-fi equipment to light up the whole room. And I think the meter scale was specified at 500 microamp or something like that for full scale. We can try measure that as well. So here I hooked up a power supply to the light, and I've put a meter across here so we can see what voltage it is. So I'm just gonna dim the light a little bit, and then we can kind of get an idea what kind of light we will get at various voltages. So here I start turning on the power supply. That's 5 volts. We can see that's actually already quite nice light. That's probably enough in most cases. So it's specified at 12 volts, but that's probably the rating of the light bulb inside the meter. I do believe it's an incandescent bulb. It's not an LED, which is nice. I kind of like the glow of the incandescent bulb. But I'll say probably somewhere around 5-6 volts. From what I see here, that's probably about the best brightness for this meter. I don't want to be blinded by my hi-fi equipment, so I'll say 5-6 volts, that's pretty good. So of course it can be a little bit difficult to see on the camera. You're not going to get the exact same brightness that I'm seeing. Okay, here I've changed the setup slightly, so move the meter to milliamps, and I put a resistor in series with the meter here. So I want to see how many microamps does it actually take to get full scale on this meter. So I'll try to turn up here the power supply. See the meter starts moving. 400. It looks to be fairly accurate with 500 microamps for full scale. That's plus 5 dB on the meter there. That is full scale, so that's looking good. The next step will be designing and building a small driver for the VU meters. I have a few requirements. It must be high input impedance so it doesn't affect the source signal, and it must run from a single supply, so for example 5-6 volts, enough to power the light. And I would like the meter to be able to reach maximum with as little as maybe 100-200 millivolt RMS signal. So I had a look around, but I didn't immediately find any circuits on the internet that matched my specification. However, I did run into this application note from Microchip, application note 1353, op-amp rectifiers, peak detectors and clamps. And it basically discusses the various ways you can rectify an AC signal, primarily for measurements. And that's really what we want. And I was thinking peak detectors, and that's how I ran into this data sheet here. So it kind of discusses all the various options. The simplest way of doing it is, of course, just using a full-wave rectifier. So we'll have our audio signal coming in here. However, since I want it to work with line level signals, we're going to have a problem with the voltage drop across the diodes. It's illustrated here somewhere. Yeah, you can kind of see it here. So this trace here is the input signal, and this would be the output signal, so we're gonna lose a lot. This is probably drawn for silicon diodes, where we will typically have a 0.7 volt drop across the diode. Well, we could use Schottky diodes, maybe we'll get like 0.3 volts drop, or we could get some exotic diodes, maybe 0.2 volts drop, but still I would like to avoid that whole drop thing. Another problem with diodes is that they're not going to be very linear. However, there's another circuit that I find much more suitable. So you can scroll down here and find it. It's the basic peak detector circuit here. So that kind of lives up to all my requirements, well, nearly. So we have high input impedance. We only have one diode here, so it works like a half-wave rectifier. However, the way the op-amp is configured here is going to compensate for the voltage drop across the diode, and then we just have a capacitor here that gets charged up, and the second stage here is just a buffer. So I think that will be a good starting point for our circuit, and I would recommend, if you're interested, you should have a look at this application note. It's quite nice. For this circuit, I decided to build a small prototype on Breadboard. This is kind of a circuit where you can only get so far with simulation, and I felt I needed a prototype to really get a feel for how it's going to work and selecting the right component values. So yeah, it looks a little bit messy with all the wires here, but we have the audio signal coming in here. We have a small electrolytic coupling capacitor here, some resistors, and our op-amp down here. So the first stage over here, the second stage over here, and this is the main capacitor, smooth out the output signal, and a couple of diodes down here for protection. So it did pay off to build this on a breadboard first, because I have made several circuit changes since the original circuit I thought it was going to work. And looking at the scope here, we can get a good idea of how the circuit is working. So the yellow trace down here is the music signal, and up here we have the outputs from the VU meter circuit. And here we see a small demonstration of what it actually looks like on the VU meter with the music signal going in. So I think it's looking pretty good. Okay, let's have a look at the design I ended up with. If we start down here with these resistors, so this is to create a virtual ground, because one of my requirements was that it must run from a single supply. Using these resistors, we will create a virtual ground, and it will work like a split supply. Usually with audio signals, you can get away with larger values resistors combined with a couple of capacitors, but in this case we do have a DC load, so we need a smaller value resistors to make the split supply have a little bit more grunt. And if we go over here, the input here, so we have our supplies coming in, and then we have the music signal coming in here. The first thing it goes in through is a coupling capacitor, and then we'll reference the signal to our virtual ground, and you'll have a resistor here. So this is just to protect the input of the op-amp in case we have music signal coming in without the circuit here being powered, or in case the audio signal coming in is way too high level for the op-amp supply. And moving on here, so we have our first op-amp, and on the output of the op-amp we have a diode here. So this basically works like a halfway bridge rectifier. Imagine we have 100 millivolt coming in here, then the op-amp will increase the output here until the negative input also has 100 millivolts on it. So that means if the diode drop here of 0.6 or 0.7 volts, something like that, will be totally eliminated, because the op-amp will just keep increasing the voltage until we have the same voltage here as we have on the input. And in case we have a negative voltage on the input here, let's say it's minus 100 millivolt, the op-amp will just produce a negative voltage here. It will try to make this input minus 100 millivolt as well, but that's not possible because we have the diode here, so it will just go all the way down to the negative rail. meaning what we get out here is just going to be all the positive peaks of what's coming in on the input here. Then we have a capacitor here, just to smooth things out a little bit. And we have a resistor here just to drain the capacitor. So by tuning these two components here, we will be able to determine how fast the VU meter is going to be reacting to changes in the signal. Then we have a couple of resistors, this 10K here and also this 10K up here. These are purely for protection of the op-amp inputs in case this capacitor here is fully charged and we power off the circuit, then these resistors here will limit the current on the inputs. Then moving further along here, we have our second part of the op-amp, and this is just to give a little bit of gain using these two resistors here. And then we have a resistor here on the output. It's just to limit the current a little bit going into the capacitor here. So this is our second smoothing capacitor. And following that, we have two diodes in reverse polarity. So this is to protect the meter from damage. If we didn't have any protection here, we could risk that maybe we'll have full voltage output from the op-amp here, and it would be way too high current for the meter connected over here. So these two diodes will limit the voltage at this point here to be somewhere between plus minus 0.6, 0.7 volt. And we have another resistor here again to limit the current, so our plus minus 0.6 volts is not going to harm the meter connected over here. And that's it. It's a pretty basic circuit, very simple, but from testing on prototype on Breadboard, this gave pretty good performance. And here we have the board layout. So I made a separate video. I'll try to see if I can link it in here on how I manufacture the whole circuit board. So if you're interested, you should go watch that after this video. I have hooked up the board here using a few small test wires, but you can kind of get the idea here how it's supposed to be mounted. So just put a little bit of double-sided tape on the back of the meter here, and then we have these 4 drill out slits here, and it just fits on the back of the meter, so be soldered in place like that, and that's it. You're done. You have the driver as part of the meter here. But I made a mistake in the layout because, well, normally I always connect through-hole components on the back side of the solder side of the circuit board. However, in this case, actually it will be soldered from the top, but since we have no through plating, there will be no connection. So I'm gonna have to change that in the next version of the board. Also, I decided that instead of using a clunky screw terminal down here, I would actually rather just have one of these little sockets here. That will also take up a little bit less space. So another change. And when I did some preliminary testing, I decided this capacitor over here, so this is the smoothing capacitor for the first stage just after the diode. The 10 microfarad I had originally designed in here is actually too big. It makes the meter movement way too slow. So to speed it up a little bit, I decided to use a 1 microfarad capacitor here instead. Other than that, I think the initial coupling capacitor for the audio signal, so this is also an electrolytic I'm using here, but actually a 1 microfarad ceramic capacitor would be just fine because it's fairly high input impedance. And we could probably eliminate the last 10 microfarad here as well. This is used for decoupling, so I think a 1 microfarad ceramic capacitor would be sufficient there as well. But I think this video is long enough already, so you'll have to wait and see these changes once I get further with the project where I'm actually going to be using these little VU meters. So I think we should just end the video here with a small demonstration of what it looks like and what it performs like.